This will be a brief introduction to Chapter 16. These handouts should be available on Canvas. This first chart on voltage and current introduces you to two terms that students sometimes get confused over. Voltage has to do with the potential energy per charge, and current has to do with the quantity of charge that might be going through a circuit. And it's very common to use water as a very imperfect analogy to current. You could be down at the arch, sitting on the steps, watching the Mississippi River go by. The speed at which the water goes by could be a function of the kinetic or potential energy that the water has. The quantity of water, the number of gallons per minute, for example, would be a function of its current. So if we use water as an imperfect example, imagine that we had a situation where we had high voltage but low current. You might recall we did the demonstration in class with the Van de Graaff generator, or maybe you've gone to the Magic House and you've seen it there. That is high voltage but very low current, which is why you were not, at least most of you, damaged by getting shocked by the Van de Graaff generator. The voltage is about 30,000 volts per centimeter. In other words, that's the amount of energy it takes for a charge to have to go through a very poor conductor like air. And in the process, of course, it ionizes the air a little bit. Sometimes you can smell the products of that ionization in the form of ozone, which maybe you've noticed before or after a lightning storm on a spring day. So the voltage for the Van de Graaff generator could be anywhere from several thousand to several million volts at 30,000 volts per centimeter of air. But it's a very low current. The current would be measured in the micro, which would be a millionth, or a milliamp. And a water analogy might be like rain. Rain is falling from a very, very high altitude. You could say it has an awful lot of energy per drop. But you don't have a whole lot of drops, even in a downpour. In other words, you can stand outside on a very, very heavy rain and it doesn't hurt your head. Now, if we talk about low voltage but high current, that would be similar to what would happen if you foolishly stuck your fingers in an electrical outlet. Something I had a student do indirectly a long time ago with pieces of tin foil that he would stick into outlets and make the tin foil touch and burn out the outlets. Believe it or not, this guy later on went on to specialize in electricity in physics. He was a little scary. In any case, the voltage in a typical household outlet is about 115, 120 volts. There's a little bit of variability there. Some of your specialized outlets in your house would be about 240 volts for things that require an awful lot of current, perhaps an electric dryer, for example. A car battery only has about 12 to 14 volts. But you might wonder, why is a car battery so big when you can think of one of those little 9-volt batteries that you can buy by the dozen at Walmart? Why does the car battery have to be so big? And the answer is that you want to deliver an awful lot of current. Each chunk of charge doesn't have an awful lot of potential energy. Therefore, it's low voltage. But household outlets can deliver up to 15 amps of current, and depending upon the electrical circuit, it might even be 20 amps. And a car battery can deliver up to 200 or 2,000 amps of current. We call that the cranking amperage because it's got to get the starter going, which has got to get the engine going. A rough analogy to that would be Niagara Falls. If you go stand underneath Niagara Falls, you can be pounded into the rock by that huge amount of water. It isn't falling from a very great height. I think about 90 meters if I remember correctly, but I'm not positive. It's not falling from way up in the sky, but it is a tremendous amount of water, even more water than the heaviest rain. Now, high voltage, high current, which I would encourage you to avoid at all costs, would be not like lightning. Lightning is got a tremendous amount of voltage because at 30,000 volts per centimeter, it's going through 1,000 or several thousand meters of air. So a lightning bolt might have 200 million volts of electricity, which is why, of course, it can be fatal if you happen to be in the conducting path of it. And it's also a tremendous amount of current, which is even a greater reason why it would be fatal. Much more so than the voltage is. And that amount of current would overwhelm your body's natural electrochemical nervous system, which involves the transfer of potassium and sodium ions in and out of neurons. That would be upwards of 200,000 amps of current. And there really is no natural analogy to this. So somewhat in jest, I put down Noah's flood. And then finally, a typical flashlight battery or a battery that's used to charge up your cell phone or something like that could be very, very low voltage. A AA, a AAA, a D cell, a C cell battery would only be 1.5 volts typically, which would be a function of the metal and the chemicals that are used to make it, if you remember your electrochemistry. And it would also be very low current as well, in the milliamp range. And so my analogy for that with water would be a squirt gun or hose or faucet. Now keep in mind that this analogy with water is very inadequate. For example, if you have a wire carrying electricity and you cut the wire, electricity doesn't leak out the end. Whereas if you were to cut the hose, water would leak out the end. Another failure or inadequacy of the water model is that when water enters the hose or the pipe at one end, eventually that water has to leave the hose or pipe at the other end as it is pushed through by the water that is behind it. However, in electricity, nothing physically actually moves through the wire. The charge is transferred by way of collisions and travels at almost the speed of light through the wire. The electrons, the mobile charged particles in the wire, barely move. And we'll be talking a little bit more about that in a later math problem. Now, the other thing I want to talk about before we go to the next page, at the bottom of this page, is the fact that a volt then is potential energy per charge. So if you think of the units, joules per coulomb, right here. And the water analogy would be potential energy per water drop. But of course, the water drops actually move. The charge is not something physical that moves. It can take 1/10 of an amp to kill a person if it goes across the heart, for example. More than 400 amps would really burn you because, of course, that's a tremendous amount of energy going through cellular material that would probably cause the water in the cells to boil. A defibrillator, used to start somebody who might have had a heart attack, cardiac arrest of some type, usually is about 1,000 volts and 25 amps on the average. Now, moving to the next page, this is a chart that you're going to see on a couple of tests coming up, making sure that you can distinguish the various symbols, units, and abbreviations we use in electricity, because they can become very, very confusing, particularly the ones that begin with the letter C. So if I can point that out, let's go to a different color. You got the word charge that begins with a C, capacitance begins with a C, current begins with a C, the symbol for capacitance begins with a C, the unit of charge, the coulomb, begins with a C, the abbreviation for coulombs begins with the letter C, so it can be a little tricky to keep all of this in mind. Another good example of why it's important to understand all the terminology on this charge is the fact that current, which begins with a C, strangely enough, we use the letter I to stand for current, and it's measured in amps, which we're going to abbreviate with the letter A. So there doesn't seem to be any consistency there. Another example would be resistance. Logically, that begins with the symbol R, but it's measured in ohms. And we use the Greek letter, omega, for ohms, and obviously not the letter O for ohms, because that would look like a zero and would be very confusing. Another thing I should point out is that there are a number of different ways in which we talk about volts. Sometimes we talk about volts and we use the letter V. Sometimes we're going to be using the script letter E, electromotive force, an old-fashioned name because volts and forces are not the same thing. But it's an old-fashioned name from 100 years ago. And we usually think about this term when we're talking about the voltage drop, and you'll learn more about that terminology later, across an entire circuit. And we use volts, or potential differences, especially when we're talking about the energy used up by various components of a circuit, like a light bulb or something. But they're all measured in volts. The last thing that I wanted to point out from this chart is all of the different names. The French physicist Coulomb, English physicist Joule, Italian Volta, Alessandro Volta. The Farad is from English physicist Michael Faraday, devout Christian man. French physicist André Ampère, German physicist Frederick Ohm. And here's an English physicist. And Tesla was in the United States, and of course now we have cars called the Tesla. And here's one of the early American physicists, Henry, from upstate New York. A lot of things in that area named after Henry. So you got a lot of famous scientists' names here. That concludes my discussion of this chart, other than to remind you that some of these terms, let's go with blue, down here, the letter B for magnetic field strength, letter L for inductance. These terms we're going to talk about in a later chapter.